Hello everybody, my name is Claudio Fantinuoli. I'm a lecturer and a researcher at the University of Mainz, and I'm head of innovation at CUDO. I'm presenting this paper also in the name of Maddalena Montecchio from the Mainz University. The title of this paper is Defining Maximum Acceptable Latency of ASR-enhanced CAI tools. Let me begin framing the experiment with the obvious question: what are ASR-enhanced CAI tools? A CAI tool, computer-assisted interpreting tool, is a piece of software that supports interpreters, professional interpreters, in different phases of their work. In particular, ASR-enhanced CAI tool is a CAI tool that integrates automatic speech recognition with the aim of suggesting in real time some information to the interpreter, specifically the simultaneous interpreter, information like terminology, numbers, and proper names. At the moment, there are a couple of ASR-enhanced CAI tools, such as Interpret Bank, CUDO Interpreter Assist, and SmartTerp, but I'm pretty sure that more are coming. The goal of such a tool is to increase quality of the interpreter's performance, specifically in the areas of the suggestions, terminology, numbers. Take numbers, for example. We pretty know from literature, but also from the daily experience, that are very problematic, difficult, a source of errors in interpretation. In this area, especially in the area of support with numbers, but not only with numbers, there are experiments that have been conducted in the past, and all these experiments seem to indicate that the use of ASR improves the quality of the rendition if compared with non-ASR. So, why system latency, and what is system latency? Latency is the delay between the spoken words, so what a speaker is saying, and the presentation in the user interface of a suggestion, for example, for the interpreter to consume it. So this is the latency, it's this delay. And a CAI tool, which works like, if you simplify it very much like I did here on the slide, you have the speaker, you have automatic speech recognition, you have some language model performing information retrieval, sometimes integrated directly in the speech recognition, but this is a very broad generalization. And then you have the human-machine interface to present the results to interpreter. In all this process, we have a delay. This delay depends on many aspects. If the tool is web-based, as most of the tools are at the moment, we have simple like network delays, bandwidth, and so on, which is always a problem. But then you have also aspects which are more intrinsic to the system. So, for example, the automatic speech recognition, which requires time to inference the transcription. For example, distinction between temporary or the final results of a transcription. But you also have aspects such as the linguistic context, which is in many cases needed by a tool in order to present the right suggestions. Think about a complex multi-token, multi-word term. You need the time to understand when the word is finished, what constitutes a word, just to give you an example. And this requires either anticipation from the machine or more context, linguistic context. Now, why is this aspect, the latency, important in this kind of tool? Because interpreters, simultaneous interpreter, work with time constraints, of course, and this delay happens also in a human interpretation, of course. This is called décalage, ear voice span. So the moment from when a word, for instance, is pronounced and when the interpreter is translated that word. And this is a very peculiar and important aspect of simultaneous interpretation. This distance in which the interpreter moves, so to say, with this span, sometimes is shorter, sometimes is longer, is influenced by many aspects. There is a lot of research in this area. I suggest you to read it from 2015, where it summarizes, among others, many aspects influencing ear-voice span. Just to name some of them, the language structure, interpreting from SVO to SOV or vice versa, speaker variables, but also interpreter attitudes, speech at the moment, density of the speech. So there are many aspects. What looks like to be common is a latency of the interpreter, which is between 2 and 4 seconds, but this varies a lot. So you can imagine, if you give a suggestion to an interpreter, you need the interpreter, the simultaneous interpreter, to be able to integrate this suggestion in the rendition without compromising, of course, other aspects of the interpretation, the flow, fluency, accuracy outside of the particular unit of interest, the suggestion. Now, what is the goal of this experiment? Is to measure how big this latency of a tool, the system latency, can be without negatively impacting the rendition of the interpreter. The hypothesis is simple like this: the system latency should be within the average AVS. But there are many aspects influencing the rendition of an interpreter in a multimodal setting. So our hypothesis needs to be verified. And why this is important for the development of such tools is because of the variables that I said at the beginning, that we need also context and linguistic context, which takes time to take informed decision to improve the suggestions. We need to know how long can be this latency in a tool to improve the quality of the suggestions, but at the same time without negatively impacting the usability of the tool. So in our experiment, we used numbers as a unit of interest, just because numbers is quite widely studied in simultaneous interpretation and in the interaction of CAI tools. We had a speech, long speech from English into Italian with what we define as an average lexical difficulty, and with 5 different latency, going from 1 second to 5 seconds. We simply let people, 8 students in the second year of training in simultaneous interpretation in a master, use these suggestions, force them to use these suggestions to measure when the tool, the latency becomes a problem. There are limits to this experiment that needs to be pointed out. We have only one language combination, meaning different language combination will probably have a different latency. We have a specific user group, which are students. However, we think that moving towards professional interpreters should only increase the latency that we measure here, the maximum latency, and not vice versa. Of course, this experiment, as I will show you a very short video, is not done in a naturalistic approach. Is very experimental. So differences may, of course, be found in a more naturalistic approach, and this is the outlook to hopeful follow-up experiments. Just to give you a sense of what the interpreters were looking at, as suggestion, I will show you a video of just a short example.
It found the unhealthiest drink was the Starbucks Venti Caramel Hot Chocolate. It contained grams of sugar and calories. AOS says it has as much sugar as 3 cans of Coca-Cola.
As you could see, highly experimental setting. We forced the interpreter to use the suggestion. This is very important. How we evaluated the performance, we had 2 kinds of evaluation. One is a stimuli-based evaluation, which is a binary evaluation, yes, no, based on the accuracy of the number rendition, the accuracy of the referent in the rendition, and the presence of disfluencies in the rendition of the unit of interest, the number, and so on. Then we have a segment-based evaluation, which is no more yes, no, by the Likert scale from 1 to 6, where we let evaluators, assess the accuracy at the segment level and the fluency at the segment level, which is more or less what we could say a sentence. The results of the stimuli-based evaluation are the follows, or as the one that are shown in the slide. We can see that we have negative impact of latency on accuracy of the number of the unit of interest, the number of the reference, and an increase of disfluency, which is of course a sign of a cognitive overload, from 4 seconds. So at 4 seconds, so after bigger than 3 seconds, we really can measure this deterioration of the rendition. As far as the segment-based evaluation, this is quite similar. So not only the unit of interest degrades, the quality and so on, from 3 seconds onwards, but also the quality, the overall quality of the segment, both in terms of accuracy and in terms of fluency. Quite evident that the fluency, which is to be expected when the results show with 4 seconds delay, which is a little bit higher than the average ear voice span, the fluency is interrupted, is deteriorated. So what are the conclusions of this experiment? Is that latency up to 3 seconds seem not to have a big effect on the rendition, which doesn't mean that we have to have such a long latency, but in our experimental setting, we could see that it did not affect very much both on fluency and accuracy at all levels. This latency is a little bit higher than what the tools that I'm aware of can achieve at the moment, which is around 2 seconds, meaning different from the perception of the interpreter. We have also studies where the 2 seconds are perceived at a very personal level as a very high level of latency. The measurements that, as far as we have done in all the studies we have done today, it doesn't look as something that hinders the possibility to successfully integrate suggestions into the rendition. So there is a difference between the perception of the user and the actual performance of the user. If you remember the lines, we have, even in our small experiment, which is of course very limited in size, observed a learning effect, immediate learning effect, meaning if at the beginning of the experiment the performance were lower, even with a lower latency, than a couple of minutes later, which is again, it indicates the need to train interpreters in the use of these tools. Of course, I mentioned the limitation of these studies, so there is a need to replicate the study with different variables, which are, in my opinion, of course, the language combinations, so that these 3 seconds could vary, could be become more precise, also considering different language combination. Very interesting is to try the effect of lexical density, let's say the complexity of the speech, different complexities on this parameter. This could also give us, in the development of such tools, the possibility to make latency dynamic, depending on the complexity of the text and the latency that interpreters have depending on this complexity. And of course, the distribution of these units of interest, it is different if the unit of interest happens in the middle of a segment, at the beginning, at the end, or the sequence of units of interest, if there are many in a unit of time or only a few. All these variables will, of course, modify the ear-voice span and the capability of interpreters to integrate suggestions into their rendition. This is the first step towards a little bit more knowledge about the interaction of human-machine in interpretation, helpful for users, interpreters, but also helpful for the development of tools which are really in line with the needs of interpreters. Thank you very much for your attention.